Igor, the floor is yours.
Thank you, Shailin. Can you hear me?
Yes, we can.
Okay, great. So now we are going to talk in more details about and you can see the screen, right?
Yes, all is good, Igor.
Okay, thank you. Now we are going to talk in more details about SYCL and data parallel C++, like because it is a heart of oneAPI idea, and it brings a great parallel programming model for heterogeneous programming, which is vendor unlocked, which means you really can use different vendors and write a single code which will run on multiple devices or accelerators. We have around 1 hour, and we will try to go over short overview on DPC++ and SYCL, and really basics of SYCL language, because the full tutorial takes usually about 4 hours, but I will give during this presentation, I will be trying to to give you all the links to corresponding materials, plus I will be more focused on some implementation specific stuff in DPC++ itself. So let's go forward and talk about what is actually DPC++ and what is SYCL. So there is an open standard which is called SYCL, which specify a standard which can be used for heterogeneous programming. This SYCL standard itself is based on ISO C++ 17 by standard. So it doesn't introduce any new keywords. It's a pure C++ language. So from this point of view, you may always think about SYCL like plain C++. And this is a link to the latest standard SYCL 2020 specification, which was published last year in close collaboration between Intel, Codeplay, University of Heidelberg, and our key contributors to a SYCL specification. And nowadays it has a range set of features allowing to do really a lot with your accelerators. So the main intention of DPC++, which is actually the compiler from Intel side, which is expected to fully support SYCL 2020 specification and be conformant with this. Unfortunately, at this moment, we are not, but this is the goal, to be standard conformant. And at this moment, current standard support in DPC++ compiler can be found here. But on top of standard SYCL support, we also deliver community extensions. And community extensions are a set of features which are bringing additional benefit to the users, but unfortunately, these are not in the specification yet. And of course, it's based on our collaboration with customers, working on real workloads where we're identifying what is missing and what can improve functionality, performance, etc., and bringing it as a community extensions, implementing it in our open source project, and sorry, and closing the loop by suggesting these extensions back to the SYCL Chrono standard. So it's actually an iterative process, right? On this slide, you can find some additional links on the Intel projects, which are open source. So as I said, the implementation of SYCL itself is it doesn't bring any additional keywords, so it's a new not a new language itself, right? by syntax at least, which means it is implemented as a set of header files. You can think about it like an additional library, right, which is shipped. And in this case, you need a set of header files which are available, and of course, a runtime support and the library itself. So, and that's why there are multiple components provided as a part of open source projects. So here you can find the compiler itself, while the compute runtime lower level API is available in the different project. And note that since we are talking about heterogeneous programming, there will be a need for some device compiler, right? And in case of Intel, there is a third project called IGC Intel Graphics Compiler, and it's also open sourced. Note that here I have been talking about open source project. However, Intel, as you know, as Shailen talked earlier, shipping all the tools in the form of binaries too, so that you can get the compiler actually from the Intel oneAPI base toolkit, right, the HPC toolkit, or you can go ahead right to the open source project and compile this code and also get a DPC++ compiler there, which is all VM based. But you need to note that the compiler which is available here, the sources of the compiler, is not exactly the same with the compiler we are shipping in oneAPI based toolkits, because in the base toolkit, this compiler has some closed source portions of the code which we are not contributing back to open source. And these portions, these parts of the code are mostly for host code performance optimizations. For example, performant Intel vectorizer is not a part of this open source project. It is available only in the closed source version of precompiled tools which we are shipping as toolkits. And this is a difference you need to know. As I said earlier, the intention by standard nowadays is to allow different backends to be supported, since SYCL by standard is an abstraction over some low-level API and some backend. So it allows you to abstract out from low-level implementation details and architecture of a device. That's why under the hood, finally, you need to have some support and some API. And historically, it was built on OpenCL. So the previous standard was explicitly saying that SYCL is an abstraction over OpenCL. However, nowadays, this there is no this limitation in the standard anymore, and it depends on the implementation of a vendor. So what Intel providing right now via toolkits, right? Because there is a difference from that point. So in the toolkits, you can find Intel compiler with OpenCL backend for, let's say, CPU and FPGA devices. And when installing additional graphics drivers, you will also install OpenCL and level 0 backend for Intel GPUs. So by installing base toolkits or HPC toolkits, doesn't matter, you're getting the support only for Intel hardware nowadays. So to get the support for more backends, like CUDA backend or also AMD backend, which is available, you need to use open source projects. So you need to take it and compile yourself, and then you can get the support for AMD GPUs or NVIDIA GPUs on top. This may be an important note because this is how you should proceed with the installation of the tools in order to get this flexibility at this moment. I'm also providing code samples links where you can find oneAPI samples we prepared for you, but also I would recommend some SYCL conformant tests, because you can see all variations of SYCL feature usage and this may be also a useful link. A few words about the packaging of a compiler. So now it may be a bit confusing because Intel ships a long list of different compilers. In principle, you need to understand that Intel right now has two major compilation technologies on the backend side. One is LLVM based, and all the new compilers which provides options to do an offloading to accelerators are LLVM based. While at this moment we still keep providing classic compiler, which were based on own Intel IL0 proprietary compilation technology, own LLVM IR, own backend, and so on. So that's why there is one set of compilers which are IL0 or classic compilers, right? And there are LLVM-based compilers like DPC++, ICX, and Intel Fortran compiler. The important note that both these compilers are actually exactly the same binary at the backend, right? So these are just two different commands how to invoke this real compiler on the backend. So which means in reality the only difference between these two commands is in the set of options which is, let's say, preset, right, and passed over to the real compiler. So for example, in case of DPCPP driver, minus F SYCL option, minus F unnamed lambdas, all paths to SYCL includes and header files are preset, right? You can get exactly the same behavior by using ICX, actually. Again, on the backend side, it's the same binary used for both these compilers. A few words about versioning. Note that versioning for classic compiler is keep going with 2021 branch right now, while DPC++ compiler or ICX has a 2022.0 version. And the confusing part here may be that the initial version of oneAPI 2022 has a versioning 0.1, while the compiler has a version 0.0. So just keep this in mind. And this link should be quite important because it shows you the installation steps required to install base toolkit and drivers. So the important part here, as I said, you can install the compiler by just base toolkit, and the OpenCL runtime for CPU device and for FPGA will probably FPGA emulator will be also installed. But the thing is that there will be no support for integrated graphics, discrete graphics without installation of the graphic drivers on top of that. And one part of compilers and runtimes for DPC++ and SYCL is coming from the GPU drivers package. That's why it is important to follow the steps quite carefully. Don't miss that the compiler GPU drivers are important since they have a part of a software stack required for execution of SYCL applications on Intel GPUs. And also important to add the user to the spatial group on Linux, right? A renderer group or video group to disable a hand check of GPU to allow the workloads to work as long as you wish and not hang and not break when system starts to think that it's hanging and not actually running. So all these steps are I explained into this installation guide, and you need to follow it very carefully. And now let's go to a real SYCL application code. Of course, it will be very simplified, the tradition code, or we can call it hello world in the GPU world, to show you the anatomy of a SYCL, the basic terms. I will be, using SYCL and DPC++ quite often as synonymous because actually, again, DPC++ is the implementation of a SYCL. That's why of a SYCL standard. That's why everything which is supported by SYCL standard is expected to work with DPC++. Not immediately at this moment, but this is a long going plans, and most of functionality is already supported. So what you need to know about the SYCL from a software programming point of view is that it's single source concept, which means both device code and host code are available in a single source file. So it's opposite to OpenCL, where you have your kernels as a standalone files, and it's closer to NVIDIA CUDA idea, right? What you also need to know is that you need to identify the host code parts and accelerator device code parts, and there are a few markers for you which may be useful. We will talk in all the details about the buffers and queues, but the thing is that each time you see the submit operation or parallel for invocation, these APIs, these calls, should be a marker for you to understand where the device code is, because the device code is this function object which is finally passed as an argument to parallel for, and it can be lambda as shown here, or you can create this lambda outside of invocation, right? Or you can pass any function object here. So this is actually a device code and or a kernel which will be executed on the target device. And the idea is that the target device may be any device. So it's not should be GPU, right? Like in CUDA, for example. You can run this kernel even on CPU or on FPGA or on GPU, which is shipped not by Intel vendor. What is also important is application scope and to understand that all kinds of scopes actually, because application scope is a usual scope, right? Coming from C++, and all the rules are applicable as usual. However, there is so-called common group scope. So it is the code which resides between submit operation and parallel for invocation. So this stuff, and common group scope is usually used in SYCL to define accessors. And we will talk about it a bit later. Just keep in mind that the common scope is this part and the device scope is this part. So it's the code in this lambda which we are passing right here. And there are limitations on the C++ standard features which you can use inside device scope. So you should be careful with what you are using in the device scope part. For example, dynamic polymorphism is not allowed here, while static is allowed. Templates can be used, but exceptions raising is not allowed inside the device code. So again, this code is not fully C++ 17 conformant in the device scope. That's why when there is a statement even in the standard that SYCL is a C++ 17 based standard, right, language, you need to keep this in mind that it is applicable to different scopes, right, to different part of your code, because there will be always a host code compiled for your host CPU, and there will be always a kernel which is not necessarily compiled for your native CPU, right? But it may be compiled for any GPU. In principle, in SYCL, there are three main memory models, right? Because we are talking about heterogeneous programming, which means you will need to pass your data back and forth from the device. Unfortunately, there is no architecture which allow you to avoid this transfers of the data, right? Yeah, there is integrated graphics, but the thing is that it's relatively small piece right on the die, and it's not so powerful as a discrete graphic card or PVC card, which can be used in data centers, right? Which should be clear that there should be a mechanism in the SYCL to allow to pass the data from the host side to the accelerator to the device side and back. And that's why SYCL provides, in principle, two major approaches. So one is a buffers, and images is a subset of buffers, so a special type of buffer. And the second one is called unified shared memory, which approach is more pointer based and very close to CUDA programming style, where you allocate the memory yourself and you have more control over allocations and memory transfers, or doing it in more explicit way, I would say. So since we need to pass our data somehow back and forth from device to accelerator and back, obviously, if we do have some data, I skipped the initialization here of this data, but it's clear. So this is some data on the host side, right? And we want to do some calculations on accelerator with these vectors on the device. So what we need to do is to wrap it somehow, right? Because the standard vector container from standard library doesn't allow you to, doesn't have features or methods which will allow you to use this data on the device side. That's why historically SYCL 1.2.1, so previous standard of SYCL, was only providing the buffer concept, buffer and image concept, where you always need to create additional wrapper, additional container for your data. And once you're doing it, you're not allowed to modify the initial data anymore until these buffers are destructive. Otherwise, the behavior is undefined. And this is still true with SYCL 2020. So we create an additional buffers. And now by using these buffers, we can operate with this data inside the device scope and device code. Well, actually, not 100% true, because you also need to create accessors in the device scope. We will talk a bit later on this. Also, and it doesn't matter that we start with buffer creation or with a queue creation. Also, what is important is to create some kind of a link with a device, right? Since we are not talking about one vendor devices only, but we talk about any device, you should have a mechanism to control which device you want to pick up from the system, right? Because on system, you always has a CPU and at least CPU available, right? And if it has a GPU, then you have a choice, and you should be able to control this. There is a special mechanism for device selections and special constructors of a device class and context class. I don't want to dive deep into these details because all this finally is encapsulated to a queue. But the idea is, by constructing a queue object, you are linking to some device. You are picking up some device or set of device, and you further, while submitting some common groups, these are called common groups. By submitting these common groups to this queue, you are initiating the process of calculations on these devices which you used. I will have a next slide talking more details and what exactly happened here when you use the default constructor. So with the default constructor, the runtime will score all your devices available on your system and pick up the most performant one. This is quite interesting and useful feature. So if you have a machine with a CPU with integrated graphics and with discrete GPU, for example, then the logic here is that the discrete GPU will have a higher score and will be used at runtime if the runtime is available, which is important. So for SYCL, since it's an abstraction, it recognizes the devices which has drivers installed and which are visible to the SYCL runtime. And that's why earlier I was talking about carefully following the steps, because this is important, because SYCL is an abstraction, which means under the hood on the lower levels, there will be lower level API and lower level implementation. So any abstraction always bring some kind of layered pie, right, in the software stack implementation. And all these APIs will map under the hood to something lower level. For example, to OpenCL APIs with OpenCL backend. You have a way to control which device to pick up into two ways. So you can, in the code, pass the device selector which you wish. You can create a custom selector based on your own logic. If you don't want to rely on this marking of devices and want to pick up the device from a specific vendor or whatever, you can derive from the device selector base class and then implement any own logic. Or you can control it at runtime. So if you use the default selector, or even if you use GPU selector, but you have different GPUs available in your system, right? What you can do is you can use the environment variable called SYCL device filter, which is a powerful way to filter the devices available on your system, devices visible to a SYCL runtime level. Always pay attention on the slides to these links I'm provided on the bottom, because they may give you a lot of additional information. Like in this case, it is a link to the very useful additional environment variables you may find. And this SYCL device filter is also there. So, and as I said, we wrapped our data to buffers, but the next step in buffer concept is also to get some accessors to this data, which means you are, in this way, you are providing to the runtime the information about the access mode in which you are going to access this data wrapped to the buffers. And this is used by the runtime to build a dependency graph. And this dependency graph will care for you about the execution order of the kernels, which means in this naive example, we have only one common group submitted to the queue and only one kernel. But in reality, you may have multiple kernels. For example, imagine kernel 1, like here, where we have for input A, B, C, and we are writing to the C buffer, right? So C is an output of this kernel, but think about other kernel which may use the C as an input data and produce E, or a third kernel which doesn't need C but need B, which we read only in kernel 1, which means the kernel 3 may be executed in parallel. So all this is done automatically by the runtime, and the correct scheduling of the kernels and possibility to execute these kernels in parallel is a task of runtime and execution graph. And that's why we need not only buffers, but also accessors. With USM, by the way, approach, with unified shared memory approach, which is pointer based, and we will, I hope, have a time to talk on this later. You will you don't need to do this. So since the data and accessors are set up, it's time to invoke a parallel for method. By the way, it's interesting to see the way how it's done, right? Because you see that there is a handler reference here. So this class, it's a handler to a common group, and parallel for is invoked as a member of this class. And there may be multiple arguments which can be passed. What is great is, again, implementation is open source, or even if you take a base toolkit, it's a set of header files. So you can find the implementation of these methods, all the overloaded versions, and understand what you can and what you can't pass. First argument is setting the iteration space or range. This is a term, and most of these terms are derived from OpenCL. And the second argument is a function object with a kernel in this case. And you need to identify somehow a piece of a data, right? Because execution concept, right, or model which is used for this kernel code is SPMD, which means this kernel instance is executed many times on GPU, right, on each execution unit in each thread. And that's why, since it's exactly the same code running everywhere, you need to identify some unique data element which you need to process. And this can be done with the arguments you are passing to the Lambda function here. And the most simple way is to pass this ID index, which just identify each element of the data you operate with inside the kernel. There are actually different ways how you can do it. And this example, again, it's quite naive, but very good to show the basics. And there are two ways how to operate with the ranges. So this one we have been using in this example is based on range class. Note that there is also NGRange class which allows you to control a bit more. We will talk about it in a few minutes. But the idea is to identify the item, the individual instance of a kernel in parallel execution. You can use ID as was shown earlier and here, but you can also use the our class, which also represents the index, but providing you a lot of additional information, like for example, if you get if you want to get some properties of execution range, like get range, for example, right? To understand inside the code, what is the wall range? With ID class, you can do this, while here you have these APIs. So it provides you more features which you can use. Now talk about a full thread hierarchy and mapping to a hardware. So the smallest instance, right, a single thread with a thread hierarchy is called work item in SYCL. It's quite similar to a thread term in CUDA, for example. And when there are all kinds of grouping of these work items to allow you to get all the features of a specific accelerators, right? If it does support CMD features or has CMD in the hardware on the hardware level, then you can group it to a subgroups, right? The bigger grouping is called a work group, right? Which can be 1, 2, or 3-dimensional set of threads. And finally, it's an NGRange, which is consisting of these work groups. And the thing is, when we are setting your range or NGRange, you can control the sizes of these work groups. So in the previous quite trivial example with a basic parallel kernels, you're just passing range and a full iteration space, but you don't control the way how this iteration space is splitted further to the work groups. It's done automatically for you. However, you have a way to do this, and this may be important to get the efficient code running on your accelerator, because as you can see, and this is the architecture of Gen 9, for example, is that you don't have one, set of execution units on your GPU usually. It is split to subparts to the subslices, each having some number of execution units, some shared resources like shared local memory, and so on. And that's why it is important to map your code, to map your workgroups to your hardware. Like this, so a workgroup are matching to a subslice and compute units, and each workgroup is executed on the compute unit, again, which consists of multiple execution units, and each execution unit has 7 threads, for example. And the subgroups is mapped to a vector hardware, right? CMD units. But I think nowadays in the SYCL standard, the constant memory was deprecated. So there are 3 standards left, 3 types of memory left. So each work item, each thread, right? It has its own private memory, which is not shared with our work item. But we know that work items are grouped in the work groups. So that's why work group allows you to have a local memory, or it's sometimes called shared local memory, right? And this shared local memory allows to optimize usage of a memory, because by doing that you avoid going to the external global memory. So as usual in any memory hierarchies, there is a fastest and smallest private memory, there is a larger but still limited shared across work items memory, and there is a global memory, right? And the idea of finally of any software optimizations for GPUs in SYCL and in principle is to efficiently use all the execution units, right? To utilize all the power of your hardware, and to minimize the memory bottlenecks, right? Which means to do this, you will probably will need to use more extensively private memory, local memory, right? Instead of going to a global memory and having a larger latency. You need to minimize data transfers between host and device, and you need to minimize the synchronization across work items, right? We will talk on that. So these are just basic principles on further software optimization. And the mechanism in SYCL which allows to construct you NGRanges, so ranges where you can choose the size of workgroups yourself, is provided by NGRange class. Again, this kind of grouping of kernels into workgroups will allow you to control better the resource usage and work distribution. And you are passing it as an argument the same way like we were doing before, but you are explicitly specifying not only the whole iteration space, global range, but also the local one and the local size. Local size is actually workgroup size. So you can say that, okay, you want to split this iteration space to workgroups consisting of 64 work items. And in that case, in order to identify the instance in the kernel code, you need to use ND item, and it provides the, let's say, well, most extensive set of features inside your device code in device scope, because here you are getting the ability to use shared local memory. You can use the barriers, and these methods are not available for regular range or item class. I intentionally highlighted this additional scope which was created in this simple example because it is important here, and the importance showing the synchronization concerns. Synchronization here means we are trying to operate and print some data back on the host side, right? And we are using the initial C vector. And as I said, once you create a buffer, you must not use this data anymore until you destruct the buffer. So that's why once the buffer is destructed, which actually guarantees the implicit synchronization, so that all queues using these buffers are finished. So that's why we are safe that the data is not calculated on the device, but it's copied back also to the host. And here we have a valid data. If we are bypassing this, there is no guarantee at all what will be printed in this way of usage, because there are different ways how to do this. And now let's talk a bit more about synchronization then. So there are two types of synchronization, right? Between the synchronization between host and device, and the synchronization within kernel itself. And within kernel, there is a way to use barriers or atomic refs actually. But there are no synchronization primitives across workgroups. And for synchronization between host and device, we already talked about buffer destruction, right? Which synchronizes the data with the host memory and cares about copied. But there are other ways how to do it, like to call a wait member function of device queue or wait member function of an event. I hope we will have time to talk about this. To use the host accessor, which is a spatial type of accessor. So before we were creating the accessor inside a common group scope, but you can also do it outside in the application scope, and it will be called host accessor. And it's a spatial accessor which is blocking the execution. And also the DAG, so the graph I was talking about, doing this kind of synchronization automatically, right? So an example of a host accessor will look like this. So we created a host accessor, and it means that here we are blocking until all enqueued kernels which working with this buffer are finished, are completed. One note which I have not said yet, I guess, is that SYCL following the asynchronous execution concept. And it means that when you are doing this queue submit operation, right, it's a non-blocking call, which means the execution on the host keep happening. So we are submitting the kernel and all that stuff, but we don't know when exactly it will be executing, right? We're just submitting this to the queue, but we keep executing on the host. And if you want to change this, host accessor is one of the way where we will block and wait, right? Here we will waiting. As I said, the other alternative is to avoid host accessor, but to invoke a wait method here, which will also block. Buffer destruction, we already talked about it. So since SYCL is following the this asynchronous concept, right? The thing is, there will be two different types of exceptions which may happen, and this is a big difference from CUDA, which is error-based. SYCL is exception-based, and that's why you need to be able to catch the exceptions in your code. And while one set of exceptions will be synchronous, failure to construct an object, for example, to create a buffer, will be a synchronous exception, and you can catch it via try-catch C++ syntax. But at the same time, there is possibility that asynchronous exception may happen a bit later, right? You submitted the queue, you submitted the common group, you keep executing your host code, and then at some moment, the execution of this kernel fails, right? But the program has already moved further to do something else. And for that, you need to create an asynchronous exception handler. the compilation and execution flow with any abstraction, right, and in heterogeneous programming world is definitely not as simple as the usual compilation. Just take a look on this part where the execution is happening or compilation is happening for the host side only, and you will see that it's quite simple flow, right? But now we are talking not about host code, but also about device code. And this device code is compiled via this flow in DPC++ implementation. So it's first, the compiler understands where in your code is the device code, right? Generate some integration header files for your host code that it can be compiled with any compiler actually. And then it take care about the SYCL device code compilation. So it is translated to LLVM IR. Then it is translated to a SPIR-V, which is important. So on the backend side, the operation is happening with a SPIR-V binary format. And then there are multiple choices in SYCL, in DPC++, how you want to work further. So you want to put, you can put SPIR-V binary to a final fed binary here, right? Wrap it somehow, but I mean, go through this path. Which means if you have a SPIR-V inline to your fed binary, you don't have a target instruction set generated by the compiler, and JIT, just-in-time compilation, will be happening at runtime for your kernels, which is very convenient if you don't know on which device you're going to run your device code, right? It will simply detect what is your device and compile at runtime. This feature is at this moment supported for Intel devices only, right? So if you use Intel CPU or use Intel GPU, this will be a default behavior actually. When you compile with DPC++ compiler, by default, the compiler for device code will generate SPIR-V and inline to a fat binary file, and it will be compiled at runtime again by JIT compiler. But you have an options to control this, and if you know where you're going to run and you don't want this runtime overhead on kernel compilations, you have a feature called ahead of time compilation, where you can specify, okay, that you want to generate the code for Intel GPU, and for example, it will be Tiger Lake architecture, and then it's done. You can also specify this, okay, it will be NVIDIA device, right? Or it will be CPU, Intel CPU. So you have these options, you have control what to do, and you actually even can mix. So you can specify what you can generate the specific target device code, but also keep a SPIR-V representation in case the device will be different. So it should also work. For more details, please refer to these quite interesting links. And I said earlier that actually any kind of abstraction results in some kind of a layered pie, right? And here you can see this pie. And there are pros and cons for this, but obviously from a developer point of view, from a software developer writing the code in C++, it's great that you have an abstraction, right? And you don't care about the underlying hardware, but you need to clearly understand what's happening under the hood, and you can see that to execute the SYCL code, you also need to have a runtime. It can be called SYCL runtime or DPC++ runtime, right? Where there is a scheduler, for example, which is scheduling the execution of kernels. There is a memory manager and so on and so forth. But on the lower level, we will always go to some kind of a low-level native runtime, which can be level 0, which can be OpenCL, which can be CUDA, which can be Rockham, and so on. Depends. SYCL doesn't limit you what will be the low-level runtime. And here the level 0 is a new standard which Intel also bringing to the industry which is open sourced and which you can also influence. And at this moment, level 0 and our implementation used to target Intel GPUs. But even for Intel GPUs, you have a choice between level 0 and OpenCL. So you can exactly the same SYCL code try to execute with a different set of low-level APIs. And this is a good, by the way, debugging hint I'm quite often using. So if something goes wrong with a default level 0 runtime, which is default for Intel GPUs now, you can switch to OpenCL backend and check what's happening there. And it can be a very good sign if everything works with OpenCL, but not with level 0, for instance, then the problem is on this level, right? Not on the abstraction level, not here, but here. So there are different techniques. And again, you can control at runtime, you can control with which backend you want to execute. You can control it via the SYCL device filter environment variable, or there is also deprecated, it's quite old, but still in place. It's deprecated, but still can be used, SYCL backend environment variable. But I would recommend to use this one as a more generic and providing better flexibility. So what it can do, it can allow you to not only specify the backend, but actually to specify, okay, the specification is happening in this kind of syntax. So you first specify the backend, semicolon, device type, and device number. And you can specify, okay, I want to run on OpenCL backend, or I want to run only on GPUs, or I want to specify the specific number of a device. So you can query all the devices available on your machine and say, okay, I want to run on GPU from level 0 backend. So this command is quite important. So each time you are logged in on a machine, doesn't matter, is it dev cloud and so or whatever, check what devices are visible to a runtime, to a SYCL runtime, right? Again, if you do have a GPU card installed physically, it doesn't mean you have drivers installed correctly or the runtime, OpenCL or level 0 installed correctly. So that's why this SYCL command is useful. It's numbering you the devices, and it's also showing the driver version, by the way, which also matters. Okay, and yeah, we talked about buffer concept, which is great, and abstraction model, but programmers likes low-level control too. They likes to have the level of control they want, and actually also simplify the porting exercises from CUDA, for example, right? And that's why there is an alternative approach which called unified shared memory, and by the name it's obvious that the idea is that we're unifying the memory between CPU and the GPU, between host and accelerator, and allowing to reference the same memory object, right? So you can use the pointer from both sides, from the host and device side, the same pointer. And there are three major models in unified shared memory. So you can allocate the memory in device explicitly, you can allocate in host, and you can allocate the data in the shared mode. And let's take on the example how it looks like. So with explicit data movement, as usual, we always need to create a queue, and then we create some array with malloc device, and then we need to explicitly copy the memory to the device, to explicitly block the execution and wait until this operation finished, and then to submit a common group and the kernel, right? Then again to wait that the data is the calculations are finished here, and then we copy the data back to the from the device to the host, right? And then wait again. So in this concept, you don't need to create buffers, you don't need to create accessors, but you're also losing some features like automatic cyclic graph creation at runtime, right? You need to care about the dependencies between kernels yourself. So you have much lower level control of the moments when the actual data transfers are happening, but you need to control and be really careful in this mode. While there is also an implicit data movement mode where you create a shared allocation, and this array, this pointer, you can use in the device code without requirement to do memory copy calls anymore. So as you can see, there are no mem copy calls anymore. So you don't need to block after mem copy, and that's why the code is more simple and there is more more the runtime doing for you than you need to care about, right? So there are more responsibilities from runtime and more help from runtime in this case. So I think that's basically almost it from my side. I also want to highlight that with USM, there are no accessors. That's why you will need to catch the dependencies using events. And actually, SYCL is event-based model, which means invoking the wait on the queue is one way, right, of doing synchronization, but it's blocking the execution of a queue of all, actually blocking the execution of all common groups submitted to this queue. While what you can do is you can catch or get an event object and synchronize on this event object. So take a look on this example where we are writing the code in a way where we put dot and then wait. So we are not writing queue.wait, right? But we are invoking this wait function in this case for the event returned by queue submit. So in this case, it actually doesn't block the execution on the host. Only wait on the queue blocks the execution on the host for the whole queue. So when you use the wait on the event, it also blocks, but it blocks only on this specific event. So once this specific kernel is finished the execution. But there is also an alternative to use the depends on method or pass the events to the kernel. And in that case, there is no blocking. There is no blocking of a host code, but there is a rule passed to the runtime that, for example, in this case, this next kernel, which by the way we named here. So you remember before we were, you've seen the code with parallel_4 without template instantiation implicit because it was a CTID feature used from C++17 standard which allow you to miss it, and actually a feature from DPC++ which allow you to use the unnamed lambdas and compiler generate the name for this lambda. So this is important because when you're going to profile your code, you want to have a meaningful names of your kernels. So there are different ways how you can synchronize, and there are effects of these ways on the performance on your application. In one case, you may call a blocking wait calls. In the other cases, and blocking calls again may block on all the kernels submitted to the queue, or may block only on a single submit operation. Or you can use these events to pass it to the kernel itself. And there is also a simplified. There is also a way to set the queue as an in-order queue, which means you are changing the default behavior. It doesn't mean that the calls will be blocking all the time, but it says that the graph which will be built under the hood will be always sequential. But this is an example where we are using the shared allocations and implicit unified shared memory concept. And since there are no accessors, the graph is not built automatically, but we are tracking the events, right? And then we are passing these events as an arguments to depends on, and we are saying to the runtime, please schedule the execution of these common groups in the following way, so that kernels A and B may be executed in parallel, but C depends on the execution of these two kernels. That's why please do it like this. And there is also a simplified syntax which doesn't require you to actually all the time write queue submit and then parallel for, so you can do a direct queue parallel for call, because again for USM you don't need this common group scope, and you can pass these arguments in this case, these events in this case, not with a call to handler depends on, but as an argument to parallel for. So this is a very short and very simplified way how to invoke in the kernel in case you use unified shared memory. So I'm on top of my hour. I just tried to collect useful links for you here. And these are the links to the open source projects, as I was talking earlier, links to data parallel C++ compiler itself, to the graphics compute runtime, to level 0 and OpenCL runtime implementation, to the graphics compiler as well for Intel devices. DPC++ book, as Shailen earlier talked, and a collection of different other quite useful links are for you here. So that's it from my side. It was quite dense, a lot of information. Next session, I will talk about porting from CUDA to SYCL. And I will show you the dev cloud and where you can find not only migration exercises, but also some very good training materials you can pass yourself and do some hands-ons as well, based on what I was talking earlier.